So in this section, we are going to analyze a probability paradox called a Monty Hall problem. It's about a game show. The host of the show is Monty, and on the stage, he has put 3 closed doors, 1, 2, and 3. And behind these 3 closed doors, he has strategically placed 2 goats, which signifies failure, and 1 swanky-looking car. And at random, he picks up 1 player from the audience and asks the audience to pick one of these 3 doors. Obviously, the player does not know what is behind these doors, and the objective of the player is to win the car. Now, at this point, Monty offers to open one of the remaining 2 doors, which have not been chosen by the player, and he shows the player where one of the goats is. And after that, he asks the player if she has had a change of mind and if she would like to switch her choice between the remaining 2 closed doors. So she has the option of sticking with her original choice, or she can change her choice and switch to the remaining 1 closed door and enhance her opportunities. So which is the best strategy for the player? Should she should she stick to the original choice, or should she flip? Let's try to simulate this problem in Python and see whether there is a strategy which can put this player in an advantageous situation. So in this section, we are going to simulate the Monty Hall problem in Python. So we start with the number of times we are going to run this simulation or play this game. So let's say we want to play this game 5 times. The win counter is initialized to 0, and win here means the player winning the car. And also the lose counter is initialized to 0. Lose means player opening any of the doors which contains goat. And lastly, we also represent the player's decision to switch doors by a Boolean variable called switch, in which if the Boolean variable switch is true, that means the player wants to switch the doors. And if the Boolean variable switch is false, then the player does not want to switch the doors. So, and lastly, we also define all the doors through a list. So we define a list for doors, which is representative of 3 doors that we are talking about, door number 1, 2, and 3. So let's start this game. We initialize a for loop, which is going to run as many number of times as we have decided to play the game. So in this case, it's going to be 5. And let's put the car behind a randomly chosen door. So to do that, I select a random number from this list, and that particular random door is then assigned to the car. Then we invite a player on the stage and ask her to choose between one of these 3 doors. Obviously, she does not know where the car is. So how it is done is that she has a random choice to choose between these 3 doors, and all 3 doors are equally probable with a probability of 1 by 3. Now, once the player has chosen the door, Monty comes onto the stage and he reveals one of the doors. So obviously, there are certain laws which he's going to follow. The first rule is that he's not going to open the door which the player has already chosen. So the player has already chosen this door. So obviously, he will not like to open this door. So this line of code represents that. And secondly, he would also not like to open the door where the car is, because once he opens the door, it's a trivial choice. The player is going to choose that door. So this line of code represents the fact that Monty will never open the door where the car is. He will always open the door where the goat is. So now, if he asks the player to take a decision whether to stick with the original choice or to switch. So this is the decision variables. In case if this decision variable is true, that means the player wants to switch. In that case, we have to define a new variable, the new choice, which is nothing. This new choice also follows certain rules. Firstly, the new choice cannot be the old choice, obviously, because we are switching. The player has decided to switch, so the old choice cannot be the new choice. And also, player cannot choose the door which has already been revealed by Monty. So these 2 lines of code, they represent these 2 rules. And if the player decides not to switch, then his new choice is equal to his old choice. Now we define the win and lose criteria. So if the new choice is same as where the car is, then we are going to increment the win counter. The player has correctly guessed the door where the car is, so she's obviously going to win. And in case if she doesn't open the door where the car is, then it's a loss, so the lose counter will get incremented. And then we are going to print some statements here and get the results out. And lastly, we are going to calculate the probability of win and probability of loss. So in this case, probability of win is nothing but number of times the player has been able to win the car, which is signified by the count in the win counter, divided by total number of times we have played this game, which is signified by numsen variable. And also we'll calculate the probability of loss, which is nothing but the count of lose counter divided by total number of times we have played this game. And we'll print out these probabilities. So let's run this game for 5 times and analyze the results. Okay, so here let me start with the first run. The car is behind door number 2. The player's original choice of door is 2. So if she sticks to this decision, she's going to win the car. And since now at this point of time, Monty comes in and he has to open a door, he can neither open the door where the player has put her finger, her original choice, and he also cannot open the door where the car is. So in this case, it's door number 2 in both cases. So he's going to open either door 1 or 3. So he's opened door number 3. Sure shot, there's a board behind it. Player's decision is not to switch. So the old choice, the original choice of door number 2 remains the same as the new choice, door number 2. And since the car is actually behind door number 2, the player wins and he gets the car and win counter is incremented. Now let's analyze the second run of the game. Here the car is behind door number 3 and the player's original choice is also 3. And in this case, Monty opens door number 2 where the goat is. Player's decision is not to switch. The new choice remains the same as the old choice, which is door number 3. So in this case, again, the player wins and the win counter is incremented. So let's analyze this case, the last case. The car is behind door number 1 and player has chosen door number 3. So Monty can neither open 1 nor 3, so he's going to open door number 2 where the goat is. And the player's decision is not to switch. And the new choice of door is same as the old choice of door. And behind door number 3, there is no car, there is goat because car is behind door number 1. So loss is encountered and the loss counter is incremented. So now we are going to run this game multiple number of times to see how it impacts the probabilities. Let's say we run it 5,000 times. And here we see that the probability of win is 0.34 and probability of loss is 0.65, which is roughly speaking, this is 1/3 and this is 2/3. And in this choice, where the player has decided not to switch the doors, the probability of win is always lower than the probability of loss. That means player is not going to is standing a lower chance of winning this game if she sticks to her decision of not switching. Does it change if she changes her decision? We are going to see that in a bit. But no matter how many number of times that we run this game, the probability of win remains lower than the probability of loss. So let's now change this decision to true. And let's again reduce the number of simulations to 5 and let's enable this print statement and analyze the game. So we run this and so now you'll see that this variable has changed. The switch decision is true. So let's analyze the first game. The car is behind door number 3. The player's original choice is 3. If she had stuck to her original decision, she would have won the car. So now Monty can either reveal door number 1 or door number 2. He chooses to reveal door number 1. Sure shot, there's a goat behind it. And the player decides to switch her decision. And she now chooses door number 2. Now the car is behind door number 3 and she has chosen door number 2. So she's not going to win. Her loss counter is incremented. Now in the second run of the game, the car is behind door number 2. The player's original choice is 1. So Monty is neither going to open 1 nor 2. He's going to open door number 3 where the goat is. And the player's decision is to switch. And after switching, the player's new choice is door number 2. Now behind door number 2, we have the car. So the player wins and the win counter is incremented. So this game runs so on and so forth. Now important part is that we increase the number of runs of this game. So I'm going to disable this print statement. And I'm going to increase the number of runs of this game to, let's say, 5,000 and see the probabilities. And suddenly you see the probability of win has become 2/3 and the probability of loss has become 1/3. Just by switching her decision to change the doors, her probability of winning has drastically increased. This is quite counterintuitive and that's the reason why it's called a probability paradox. And no matter how many number of times you run the simulations, we can run it, say, 1 lakh times. And the results are going to be the same. We're going to run it, say, 2 lakh times. It's going to take some time, but this doesn't change the probability. There we are. So 2/3 probability of win, 1/3 probability of loss, and this change in probability of win has happened by a very simple decision of making sure that no matter what was her original choice of the door, if she decides to switch the door, her probability of win in the larger scheme of things, in the larger simulations, a larger run of games, her probability increases to 2/3. Probability of win increases to 2/3, and her probability of loss reduces to 1/3, 1/3.